Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to walk you through how to rank relative strengths of acids and bases. The skill of ranking acid and base strength is unfortunately something that many students never learn, and the reason why is because most textbooks and professors do not provide very clear instructions on just how it's done. So I've created a problem-solving process to really make this a lot simpler for you. The first step in the problem-solving process is to draw the conjugate base for each of the acids that you're trying to rank qualitatively. That's because we don't actually ever want to rank acids directly. You'll run into too many problems if you try to do this, so just draw the conjugate base for each of the acids first and foremost. Next, we're going to write out the following two statements. The stronger the acid, the weaker or more stable its conjugate base, and the weaker the acid, the stronger or less stable its conjugate base. Step 3 is to rank the stability of the conjugate bases according to the following factors: element, also known as atomic effects, inductive effects, resonance effects, and hybridization, sometimes called orbital effects. We'll go through what each of these are later in the video. Last up, we're going to reach a conclusion about the acids by comparing our results of step 3 with the statements that we wrote in step 2. Now, I do want to point out one more thing, and that is there are other factors that will affect the stability of a base. One important one is aromaticity. However, this is typically covered in the unit on aromaticity, not in the introductory acids and bases unit. Overall, what I want to emphasize is that, again, you shouldn't try to rank acid strength directly. Rather, you should always focus on their conjugate bases. The most important step here is actually writing out the statements about the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger its conjugate base. Students who skip this step, even if they do every other step correctly, often make mistakes at the end of the process. So actually writing this down when you're going through the problem-solving process is going to help you avoid easily avoidable errors. Before we do a deep dive of the 4 factors mentioned for step 3, it's very important, crucial even, that you understand what weak means in chemistry. So if you think about a weak reactant, let's take a weak acid for example, you would say that it is less reactive than a strong counterpart. So for example, a weak acid is not going to give up its hydrogen as readily as a strong acid. So a strong acid is more reactive and a weak acid is less reactive. So weak in chemistry means less reactive. Of course, it's easy to make the jump from less reactive to our next synonym, which is stable. If a reactant is less reactive, of course we say that it is a stable reactant. It's not readily going to transform into anything else. It's not going to cause a reaction with another molecule, so it's stable. Now, it's less intuitive to make the jump from being weak to being stable. In fact, this is very counterintuitive for most students. However, it makes sense that something weak is less reactive and that something stable is less reactive. So you can conclude that weak and stable in chemistry actually does in fact make sense. But why it's not intuitive is because most people think of something strong as stable. In everyday language, this makes sense, especially if you think about the foundation for a house, for example. A strong foundation for a house means that the house would be stable. But in chemistry, it's actually the exact opposite. Our final synonym here is delocalized. Since we'll be analyzing bases for most of this video, let's think about what a base is. A base has a lone pair or a pi bond or a negative charge. Now, if we can delocalize that region of electron density, and by that I mean spread it out across a much larger area in the molecule, that means we're going to weaken that charge by spreading it out. That's what we mean by delocalized. So, weak in chemistry means less reactive, stable, or delocalized. Now that we understand that weak and stable mean the same thing in chemistry, we can focus on the strength or stability of the conjugate bases. So let's first talk about element effects. Element effects refer to what atom the lone pair or negative charge is found on. Now, there are two definitions of a base to keep in mind when thinking about element effects. The first, of course, is that a base is an electron donor. In other words, it likes to give up its electrons. The more readily something gives up its electrons, the stronger it is, or the less stable it is as a base. Next, we can refer to a base as a proton acceptor. In other words, a negative charge that is better able to attract a positively charged proton is a stronger or less stable base. So what we're going to do is we're going to use periodic trends to evaluate element effects. First, we need to understand the left to right trend. And the left to right trend is explained by electronegativity. An atom that is more electronegative wants to keep its electrons, not donate them. So from left to right on the periodic table, since electronegativity increases, basicity also must decrease. Now we can talk about the top to bottom trend. This trend is explained by size. Valence electrons are farther apart in larger atoms. This delocalization of electrons makes it much harder to attract a proton. Therefore, when atomic size increases down the periodic table, basicity also must decrease. The second factor that we consider when evaluating the strength of a base is inductive effects. Inductive effects refer to electronegative atoms pulling electrons towards themselves, thus delocalizing electron density around nearby atoms and weakening a base. There are a few factors that increase induction. First is the electronegativity of the atom. So I have a table of electronegativities down on the bottom of this page here. Obviously, something that is further to the right and further up, which is our trend for electronegativity, is going to have more of an inductive effect. Next, we need to consider the proximity of the electronegative atom. An electronegative atom that is a lot closer to the lone pair or negative charge, or the base that we're evaluating, is going to have more of an inductive effect. And last, we refer to the quantity of electronegative atoms. So more nearby electronegative atoms will have more of a delocalization effect. So let's consider the following. If we look at these four bases, the base is found at the oxygen position. That's where our negative charge is located. So element effects, which we reviewed in the last slide, refers to the oxygen only. Inductive effects refers to the nearby electronegative atoms, in this case either chlorine or fluorine. We have increasing stability from left to right in this picture because what we're comparing in the first one is the chlorine versus the fluorine. You can see that we are 2 carbons away from that negatively charged oxygen for both the chlorine and the fluorine in the first 2 molecules. So the difference is that chlorine is less electronegative than fluorine. That makes the molecule with the fluorine more stable because it delocalizes that charge more because it pulls the electron density further away or more strongly away from that oxygen. The third molecule is more stable than the second molecule, and that's because that fluorine is only 1 carbon away, so it's a lot closer. And lastly, the molecule on the right, which has 2 fluorines, we simply have a greater number of nearby electronegative atoms, thereby increasing the stability even further. The next effect to analyze when discussing the strength or stability of a conjugate base is resonance effects. Resonance delocalizes electrons among adjacent p orbitals, thereby weakening or stabilizing a base. When we refer to resonance effects, quality matters the most. So resonance structures that place a negative charge on an electronegative atom, such as oxygen or nitrogen, have more of a stabilizing effect than resonance structures that place a negative charge on carbons. If a molecule has more resonance structures that can be drawn with negative charges on oxygen and nitrogens than another molecule, then its resonance effects will be more stabilizing. That doesn't mean that quantity doesn't matter. Being able to spread electron density over a greater number of p orbitals still helps delocalize electrons. So being able to draw additional minor resonance structures by placing electrons on other atoms still has an additional stabilizing effect. It's just that quality matters more. So being able to draw more major resonance structures has more of an effect than just being able to draw a greater total number of resonance structures. Let's look at this example. I have 3 molecules here, and you can see that there's increasing stability from the one on the top to the one in the middle to the one on the bottom. Why is this? Well, if we analyze the first one, we can draw one resonance structure. And the resonance structure on the right puts a negative charge on a carbon. That means it's a minor contributor to the resonance hybrid. So the only real major contributor is that one on the left. So this would be more stable than just having an O negative without the double bond next to it, because there is a resonance structure, but that stabilizing effect is minimal because the other resonance structure is a minor contributor. For the second molecule, if we draw the resonance structures for it, we can draw 3 additional structures. That makes it more stable than the original molecule, which only had 1 additional resonance structure. However, that second molecule, even with 3 additional resonance structures, it still puts the negative charge on carbon 3 different times. So we would say that there's 1 major contributor to the resonance hybrid for the second molecule and 3 minor. The molecule on the bottom is the most stabilized through resonance, and that's because its resonance structure also puts a negative charge on an oxygen. So here, even though there's only 2 total resonance structures, both are major, which means that that electron density is very well spread out in that molecule. The last factor to consider when evaluating the stability of a base is hybridization. In particular, we're referring to the hybridization of the atom that carries the lone pair or the negative charge. Compared to the long and dumbbell-shaped p orbitals, s orbitals are small and spherical. That means that sp orbitals, which have a 50% s character, are going to be shorter than sp3 orbitals, which have 25% s character, because they get half their shape, rather than just a quarter of their shape, from the smaller s orbital. When comparing like atoms with a negative charge, and with all the other factors being equal, the atom that has the greatest percent s character will be the most stable or the weakest, because its electrons will be closer, and therefore more attracted to, the positively charged nucleus. This makes them less available to be donated, and since one of the definitions of a base is an electron donor, we're going to be less basic if we're more tightly held by the nucleus. So if we look at the following example here, I have a negative charge on the end of an alkane versus a negative charge on the end of an alkene versus a negative charge on the end of the alkyne. With the alkane, that carbon on the end that has the negative charge is sp3 hybridized and it only has 25% s character. The sp2 hybridized carbon with the negative charge has 33% s character, and that sp hybridized carbon on the triple bond has 50% s character. Following our trend for hybridization, we have increasing stability with that greater percent s character. Now that we've learned all of the factors that we need to determine the strength of an acid or base, let's go ahead and put this all into practice. So I have a molecule here, and what we're going to do is rank the labeled acids, or in other words, the labeled hydrogens, in order of decreasing pKa. So what does that mean, decreasing pKa? Well, a lower pKa means a stronger acid. So essentially what we're going to be doing here is we're going to be putting these in order from least acidic to most acidic. And if we remember step one says that we're going to draw the conjugate bases for all of the acids. Now this is one molecule, so what I'm going to do, I'm going to kind of use a cheater shortcut here. I'm not going to draw this molecule 5 different times. I'm going to draw it once, but I'm going to draw it where I remove the hydrogen from each of those positions and replace it with a lone pair. That way I'll be showing all of the conjugate bases all simultaneously. So I'm going to go ahead and draw that. So now step 1, draw the conjugate bases. is complete. Step 2, we're going to write out our statements. So now I've written out the stronger the acid, the weaker or more stable its conjugate base, and the weaker the acid, the stronger or less stable its conjugate base. Now we're going to evaluate these conjugate bases based on those 4 factors that we talked about. Let's start with element effects. For element effects, again, we're looking at the atom that the negative charge is directly found upon. And for this step, we're going to make sure we're not going to have any confounding variables that we're looking at here. So we're just looking at element effects in isolation here. So since the lone pair for 1, 2, and 3 are all found on carbons, we're going to say that those are equal to each other with element effects. The lone pair on 4 is on a nitrogen, so that's going to be the next most stable. And then the most stable is going to be the lone pair found on that oxygen, or 5. That's because from left to right on the periodic table, you increase electronegativity, and when you increase electronegativity, you are stabilizing that negative charge. Next, we're going to look at inductive effects. So again, we're looking for nearby electronegative atoms. Now for carbons 2, 4, and 5, we're not really going to say that we have inductive effects. What we are going to say is that we do have some resonance effects, so we're going to ignore the fact that there's a nearby oxygen that's the same distance away from those lone pairs in all of those. So again, we don't really care about inductive effects for those. Now for 1 and 3, 3 is between 2 oxygens, or rather between 3 oxygens, but it's kind of far away, and 1 is only close to 1 oxygen. So inductive effects aren't going to matter all that much for this particular problem. They have an effect, but it's not going to be a big enough effect to override the other factors. So we're going to say that inductive effects are negligible across the board for this molecule. The third factor we're going to look at in this molecule is resonance. Notice that the lone pairs on 2, 4, and 5, they can do resonance with that nearby carbon-oxygen double bond. So in all cases, we can draw a resonance structure. So I'm going to go ahead and at least show the arrow pushing for those. What we see here is that obviously 1 and 3 have no resonance structures at all, so that's irrelevant with resonance effects. But 2 has 1 major structure and 1 minor resonance structure. So that's going to have less of a stabilization effect than 4, which is going to have 2 major structures. And that's going to be less effective at stabilizing the negative charge than 5, which also has 2 major resonance structures, but it's a more even split because it's between 2 oxygens rather than an oxygen and a nitrogen. Last, let's look at hybridization. Notice that with all of these conjugate bases, the only one of them that is found on an sp3 hybridized atom is the very first one. Atoms 2, 3, 4, and 5 are all sp2 hybridized, with 2, 4, and 5 being sp2 hybridized because the lone pair on each of them is found adjacent to a p orbital. With 3, the lone pair is directly found on a carbon that has a double bond, so that one is also sp2 hybridized. Therefore, according to our rules for hybridization, increasing %s character increases the stability of the base. So now that we've gone through all 4 of these factors, now we can put it all together. So we're going to use our rankings from step 3 and compare that to our statement from step 2. So the stronger the acid, the weaker or more stable its conjugate base. And in every case, outside of inductive effects, which we said were negligible, number 5, conjugate base number 5, was the most stable in every situation. That means that acid number 5 is going to be the most acidic because it has the most stable conjugate base. So the most acidic is acid number 5 on the original drawing. We can then say that 4 is going to be the next most acidic. That's because in all the other cases, conjugate base 4 was the second most stable. Now let's go to the other side. The weaker the acid, the stronger or less stable its conjugate base. It looks like for element effects, 1 was the least stable. For hybridization, 1 was also the least stable. It had nothing with resonance, and again, inductive effects were negligible. So the least stable, or the strongest base in this situation, was 1, which means that acid number 1 must have been the least acidic because it had the strongest or least stable conjugate base. Then when we compare 2 and 3, 2 had the stabilization from resonance. 3 had no resonance. So that means that 2 was the most stable conjugate base when compared to 3. So that means that conjugate base number 2 being more stable than conjugate base number 3 means that acid number 2 was more acidic than acid number 3. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.